Hello! Today we'll be talking about the group 14 elements of the periodic table, also known as the carbon family. Specifically, we're going to explore how its periodic trends influence their reactivity and behavior, explain their relationships with other groups in the periodic table, and showcase how these unique properties make them invaluable in real-life applications. Starting with periodic trends, the first one we're going to discuss is the gradual transition to metallic character. At the top of the group, we have carbon, a classic nonmetal that exists in several allotropes like diamond and graphite. Moving down, we encounter silicon and germanium, which are metalloids, elements that show properties of both metals and nonmetals. And finally, at the bottom, we find tin and lead, which are definitively metallic. This transition reflects a fundamental principle. As atoms get larger and outer electrons become less tightly held, metallic properties become more pronounced. Speaking of atomic size, there's a clear increase in atomic radius as we move down the group. This happens because each element adds a new electron shell, making the atoms progressively larger. For perspective, carbon's atomic radius is only about 70 picometers, while lead's is nearly twice that at 175 picometers. This size difference dramatically affects other properties, which we'll see in the next slide. The ionization energy trend is particularly important to understand. As we move down from carbon to lead, it becomes progressively easier to remove an electron from these atoms. Why? Well, there's two main reasons. Firstly, the outer electrons are farther from the positively charged nucleus, and secondly, there are more inner electron shells shielding the outer electrons from the nuclear charge. This explains why carbon has an ionization energy of about 1086 kilojoules per mole, while lead's is only about 716 kilojoules per mole. Electronegativity follows a similar pattern, increasing as we move up the group. Carbon, being the smallest, has the highest electronegativity at about 2.5. Its small size and relatively large nuclear charge gives it a strong pull on shared electrons. By contrast, lead's electronegativity is only about 1.8, making it much less likely to attract shared electrons. Closely related to electronegativity is electron affinity, the energy released when an atom accepts an electron. Carbon shows a high electron affinity at about 122 kilojoules per mole. As we move down to silicon, germanium, and tin, we see a slight fluctuation, but the general trend is a decrease in electron affinity. Lead has an even lower electron affinity, making it less likely to form negative ions. This pattern makes sense when we consider atomic size. Since carbon has the smallest atomic radius, any added electron would be close to the nucleus and feel a stronger attractive force. The melting and boiling points show one of the most dramatic trends in the periodic table. Carbon is an outlier with an extremely high melting and boiling point. Its melting point is over 4,000 degrees Celsius. This is due to its unique ability to form strong covalent network structures. Moving to silicon, we see a significant drop, but still high temperatures, with a melting point of 1,420 degrees. This trend continues downward through germanium, tin, and lead, with lead melting at just 327 degrees Celsius. This pattern reflects the changing nature of chemical bonding in these elements, from strong covalent networks to metallic bonding.
Discussing the major reactions and formations of the group 14 elements, we must first talk about their reactivity. As we move down the group, the reactivity and metallic behavior of the elements increase since the size and distance of the outermost electrons and nucleus increase. We also find that because of similar reasons, the inert pair effect becomes apparent for the elements going down the group 14 elements. The inert pair effect is a phenomena where the outermost s orbital electrons don't participate in bonding, leading to structures such as tin chloride and germanium chloride. Carbon alone has some interesting formations as it has allotropes, being physical forms. These physical forms are diamond and graphite, which are either entirely rigid as diamond formation or free-moving in composition like graphite. And another way to say that, graphene can also form nanoribbons, which can then be turned into nanotubes. These structures have interesting energy levels because they display properties that make them more similar to semiconductors. Continuing on with formations, germanium and silicon crystallize in a diamond structure, similarly to carbon. Tin, on the other hand, has two allotropes, alpha a brittle white powder, and beta, a silver metallic substance. Tin, entirely metallic in its composition behaviors. Getting into the major reactions the group 14 elements can participate in, the very first we will discuss is combustion, as shown in the first figure. This reaction is one of the elementary reactions that we learn in high school chemistry, not because of its general importance, but display of carbon reaction behaviors. Adding to that, we can bring up the reactivity of the group 14 elements with halides to form tetra or dihalides. The center figure shows silicon tetrabromide. The group elements have a tendency to form dioxides as well, which variably react with acids and bases following their formation. On the right, we can see a carbon dioxide. Group 14 contains some of the most abundant elements on Earth, so its reactivity can have endless discussion.
The group 14 elements are interesting in that they span the range of metallic behavior. Carbon, like the noble gases, most of the halogens, and other important organic elements like nitrogen, hydrogen, oxygen, phosphorus, and sulfur, is a nonmetal. Silicon and germanium are metalloids, an intermediate category that includes boron, arsenic, antimony, and tellurium, while tin and lead share all the common traits of metals. One specific relation of silicon to certain elements in groups 13 and 15 is in semiconductors. Group 13 elements like aluminum, gallium, and indium effectively raise the valence band of silicon, while group 15 elements like nitrogen and phosphorus lower the conduction band, yielding a smaller band gap. As metals, the properties of tin and lead can be combined synergistically with those of other metals when combined in alloys. Beyond the centrality of carbon in all of organic chemistry and biochemistry, a particularly new and unique application of carbon is in endofullerenes. Endofullerenes are spherical carbon constructions with small molecules trapped inside. In medicine, endofullerenes have served as MRI contrast agents, X-ray imaging agents, and as radiopharmaceuticals. Silicon and germanium are used as semiconductors, among other things. Silicon-based light-emitting diodes, or LEDs, in computer processors exemplify the ubiquity of this element in modern life. Common uses of tin include bronze, while lead finds use in batteries, ammunition, and other alloys. To close, here are a few fun facts that we found relating to some Group 14 elements. An interesting development in the application of carbon chemistry involves carbon nanotubes. Carbon nanotubes are made from graphene, which is an individual layer of graphite wrapped into a long cylinder, which can be made to vary in diameter. Nanotubes with a narrow enough diameter are semiconductors like silicon, and for a long time it has been speculated that such semiconductor nanotubes might replace silicon computer chips when their limit of miniaturization has been reached. Such speculation has recently come a lot closer to realization as a team of MIT researchers successfully built a 16-bit processor sophisticated enough to run a program that output the message, "Hello world, I am RV16X Nano made from carbon nanotubes." While far from competing with today's processors, it's a step along the path that will eventually lead to processors 10 times more efficient than their silicon counterparts. In the realm of spin-based quantum computing, germanium has recently been demonstrated to have advantageous properties. A new field, spin-based quantum computing, uses the two states of electron spin, up or down, to represent the 0 and 1 of binary information coding. By manipulating electron spin, quantum calculations can be performed. Due to its strong spin-orbit coupling, large electron wave function, and high mobility relative to silicon, germanium may come to occupy a larger role in the development of this technology.